Let me share my screen. So yes, we have a very polyglot environment, and I would like to tell you the story how it became so and what challenges we faced. I will first tell you about what we are doing and what is the business we are in, and also what the system looks like in general, and where Kotlin is plugged into this, and then finally what challenges we faced. I'm a Kotlin user since almost the beginning, and I'm using it to solve various engineering problems. That's my go-to language on the JVM. That's why this project is also started on Kotlin. At Ekata, where we build the system, we do identity verification. I will tell you what is an identity verification scenario, but it basically means that we have an API, what is called by merchants and other companies who are dealing with users, and they wanted to identify their identity or wanted to check the identity they provided is actual valid. We provide a lot of signals to them, but we also wanted to make a machine learning solution to provide a single score to the users, because it's easier for a lot of them to process. They don't have machine learning department to build their own models. So what is our business? If you shop at online merchant, most probably you will provide your email address, phone number, shipping billing address, or other identity elements. And the merchants are checking it via fraud platforms or directly with an identity check provider like Ekata. And what we are doing is that we match these identity elements against our identity graph database or against the historical transactions we have seen. And then we return a score or we return these signals, and then based on that, the merchants are making a decision whether they ship the product or not. So if they are not sure about the identity, it might be a credit card fraud or other fraudulent activity, and so they don't want it to lose money and the product, so they don't ship. If you are not familiar with how machine learning looks like in general, it's basically crunching data, and then you're training a model on the data, and then the model is used to make predictions. So that's the basic machine learning lifecycle. And then you evaluate your model, and if it's not good enough, then you go back and try to create different models. The first step of this is called feature extraction. This is when we take the data as it is from the data source, and then we convert it into a format which is suitable for training and making predictions. It's very important that this method, these transformations, are the same when we are making the training and when we are doing the prediction. The model is then shipped to into the product environment, and it's also very important that it behaves the same in both systems. So our approach was that because our production system was written in Clojure, and there was no data processing environment at that time at Ekata, I was writing my system in Kotlin. So I was reading the data in Kotlin. I was extracting the features with the feature extraction library, and I was training a model, and I wrapped the whole thing into one single model. And because our target system was also JVM, we were able to ship it together, and it was very easy to integrate for the engineering teams. It's also worth to mention that to have the very same feature extraction in production and during training, we describe the feature transformations as data, and then the same code is running in production and in training to do those transformations. Currently, so the first system of our system was not using Spark or any big data things because we didn't have that much data, so it was just a simple Kotlin application. And then as the amount of data evolved, we needed something to make it more distributed and more efficient. And so we started to transform our systems one by one into Spark components, which means that because Spark is written in Scala and our machine learning library is written in Kotlin, we have to interact with Spark code or Scala code. Therefore, there's a new interface, an interaction interface for us to be able to talk to those components. Also, the result of a training is a machine learning model, and we encapsulate it with the machine learning library, the Kotlin machine learning library, and we ship it into production. And then they embed it into the Clojure microservice architecture. So the whole pipeline and the whole system was basically designed backwards from this because we wanted to have a very easy integration. This was kind of a proof of concept project at the beginning, so it was not possible to rewrite everything. So we wanted to have something which is ready to ship. And by encapsulating our Kotlin code with some data, how to transform that data and how to make predictions on that data, they were able to simply instantiate a predictor class. So this predictor class, what you can see in this Clojure code, is from the Kotlin library, and also they just call it with the data. It looks a bit complicated because this is how Java interop looks like from Clojure, but this works perfectly, and it's just a function call for them. It's pure JVM. There is no native code embedded, and it's just a jar what they have to include, and it's self-contained with the data and the code. So, as I said, we were started from having a single Kotlin pipeline to train this model, and we had the Kotlin library to encapsulate it with the model data. But as the amount of data grew, we had to rewrite everything around the Kotlin core into a distributed system which uses Spark. So we read the data from S3, we do the feature extraction in Spark, we do the training in Spark, and we do the evaluation and encapsulating the model in Spark, but the resulted model is not dependent on Spark. The original project structure was very close to what you've seen on the previous picture. So we had the modules, like the feature extraction module, the training module, the evaluation module, and it's kind of natural that they depend on each other. So the training depends on the feature extractor, and evaluation depends on the training. What we also did is that unfortunately, it was not possible to put Scala code and Kotlin code into the same module, the same compilation unit. So we all these modules had submodules for the Kotlin code and the Scala code. And the Scala code was basically just used to as a glue code to interface with Spark, because Spark depends heavily on the type system of Scala. So sometimes it was necessary for easier interaction to write some glue code. And it was a pretty static code base. It didn't change much. Most of the coding was in Kotlin. So we had a one-way interoperability. Only we called basically Spark functions from Kotlin and other Kotlin functions from Kotlin in other modules. The code started to evolve. More people get involved. They rewrote some part of the system into Scala because of performance issues, or it was easier to interact with the Spark code that way. So then we started to have dependencies where the Spark code was calling the Kotlin code, and it basically meant two-way interoperability, and it started to complicate things a little bit. So what challenges we basically had when we try to integrate Kotlin into this whole system? So the first one is a pretty, it seems like a very simple issue, is that Spark is a data manipulation framework. And and it has a SQL-like interface as well, where you can do selects and other things. So, for example, a select has an arbitrary number of arguments. It is implemented as a variable argument function in Scala, aka Vararg, and these Varargs are Scala specific, so they don't have the classic Java implementation, or the bytecode which is compiled from the Scala code is not similar to the Java one. They use a sequence instead of arrays to represent the parameters. That said, they thought that somebody wanted to call these functions from Java or other languages. They have an annotation called at Varargs, and then it basically creates an alternative function with the classic Java interface, and it's as easy to call it from Kotlin as from any other language like Scala or Java. Fortunately, the Spark interface is mostly annotated, but in some cases it was not. So if you see the Scala function in the top right corner, it's I called it classic, so it doesn't have the annotation, and it looks exactly the same as the other one, but it's not possible to call it from Kotlin because it doesn't seem like a Vararg for the Kotlin compiler or for the Java compiler. What we can do is with Kotlin extension function, actually, we can hide the conversion and everything needed to call that function. Because what we have to do is basically we have to convert our Vararg string array to a list, and then that list into a Scala buffer, and the Scala buffer to a sequence. And then that sequence can be passed to the function. So with this extension function, we can just call it the same way everywhere in the code where we include this extension. So extensions, we found that extensions are very useful for dealing with Scala code in general, actually. The second thing the second challenge we faced is that Spark is a data processing tool, so it has many transformations. You can filter data, you can have string transformations, numeric transformations, mathematical functions, whatever. But sometimes it is necessary to have a custom transformation, which is basically Java or Scala code, and we wanted to execute that Java or Scala code on a certain column in the columnar data. This is called UDF in Spark. It's called user-defined functions, and the interface in Spark is basically a Scala function. You pass in a Scala function, and that Scala function will be executed, or you can call it Clojure or Lambda. So like this function here is called a Lambda. First parameter is a Lambda function, the second is a string, and it basically calls the Lambda function with that string and gives back the result. So if it's Scala, if it's above 2.12, Scala 2.12, it's very easy to call it from Java or Kotlin. You just simply pass in a Java Lambda or a Kotlin Lambda, and everything is fine. Because there's an interface in the background called function n, so function 1, function 2, function 3, depending on the number of the parameters. So it's a Scala interface, and Scala uses it to represent the Lambda. And the SAM, the single abstract method interface in Java is basically that if you have an abstract class or interface with one single one single function to implement, then you can use a Lambda to implement that. So these Lambdas here, the Java Lambda and the Kotlin Lambda, are basically compiled into a function one Scala object automatically. This is very neat, and we can use it in a lot of places. And so with that one, we can use Lambda functions from Kotlin like they would be Scala Lambdas. The problem with this is that it's very nice in 2.12, so you can even pass a method reference instead of a Lambda, or you can have the function one object passed around in your Kotlin code like it would be any arbitrary object, and then you can use it when you want. But the problem is that in 2.11 it's not possible, but because they don't implement the SAM interface, and so you have to make this anonymous inner class, and it's very, very ugly. But it also works this way. Obviously, extension functions can also help for us. You can Kotlinify that call by wrapping the whole object creation into a function, and then in the rest of the code, it looks like a normal function call. Also, Lambda SAMs are not implemented in 2.11, but so Spark has a Java interface as well. So there is a user-defined function object, and because it's Java, it is SAM compatible, so we can use that. So it was also a solution what we did that just use that Java object. The only thing is that because the type inference system is not working on that, we have to specify the type of that for Spark. So it was also good to use extension functions, and it saved us. But also Java objects are also come to the rescue a lot of the times, and this chain of automatism is very nice. So there is a Kotlin Clojure, which will be a single abstract method, which is basically a Scala function object, which is a Scala closure. So through this, there's a lot of things that can be solved easily. We will see examples for that. The next thing is a bit different because it's not really about the language itself or what code is compiled. It's more like a technical issue. I will talk about why it is needed, but in Spark we need a lot of serializable data. So basically everything what is in a Spark code should be serializable objects. So we were surprised. We were looking for some very weird errors, and we wanted to know the root cause, and we realized that some lists in Kotlin are actually not serializable. So if you have a list of strings or any objects, and then you take a sublist of it, the sublist won't be serializable. It will be an immutable on-the-fly object, and so it's not serializable. Also, the S reversed is creating a view, basically, which is not serializable. On the contrary, the reversed function in the bottom code example you can see, that is serializable because it creates just another array list. And also, this was our main issue, actually, that we use a lot of primitive arrays in the machine learning code. And if you have a primitive array, so a non-reference type array, and you use the S list on it, and it will create a list view, but it's also not serializable. And the interesting thing is that if you use it on a reference type, it is serializable. So it's not uniform across the two different type of arrays. And also, if you use the toList, then it also creates a copy, so it is serializable. So why it is important to be serialized, to have serializable objects. So if you have a Spark cluster, it consists of a driver and several worker nodes. These are different computers, and or can be. And on the Spark driver runs your Spark program. The Spark program is doing like selects or filters the data, and all of those, or transforms the data, and all of those steps are tasks. And these tasks are distributed among the workers. And the data is also distributed among the workers, and each worker is executing the tasks on a subset of the data. But to be able to do that, you have to distribute the task from the Spark program to each worker. And that's where it involves serialization. So the task is serialized and copied to the worker, and also the parameters, what is passed from the Spark program to the task, they should be serialized. And that's where there can be weird errors if if you use some Kotlin structures, then they tend to create nested maps which were not serialized and nested arrays which are not serialized. So actually Spark is checking for this interface. It is not using Java's object output stream or any Java built-in serialization, but it is checking for this interface, and it's important to know that you have to have it. And also the collection functions in Kotlin are not very uniform, whether they are creating a new collection or they are creating a view. Some of them are serialized, some of them are not. The next thing is what was causing some really weird and silent bugs, and it was very hard to find it, is number types or primitive types. Because Scala and Kotlin have a very different philosophy about these types. So the scala.Double is not a reference type. In Scala, there is the AnyRef and the AnyVal, and they have a common any type, which means that double is an AnyVal, which means that it cannot be basically null. So it is not a reference, therefore it cannot be null. Of course, it's implemented as an object under the hood. So it is probably the compiler which makes these transformations. But if I try to cast null into double, then it will be 0 basically. So in the background, somehow my null object becomes a 0, and it is problematic for us because we encode missing values as nulls. And the missing value and 0 is not really the same. The interesting thing about scala.Double is that in Kotlin, so if you access the scala.Double from Kotlin, it can be easily null. So it can have a null value, as well as Java.Double. So Kotlin.Double and Java.Double are not exactly the same things, as well as scala.Double is also different, and they behave slightly differently. So if we have a null value in JSON and we deserialize it into a simple double, Kotlin.Double, which is a non-nullable double, the same thing will happen to us as happened in Scala, that it will be a 0. And that's also a side effect that we just realized. So my assumption was that this code should be throw an exception that the value I read is a null and this type is not able to hold a null. But what happened is that it was converting it to a 0 without any errors. The Java.Double, we already discussed, it's not doing that. If we wanted to deserialize it into a nullable double in Kotlin, it's not that easy. It's because of Jackson's serialization interface. We have to wrap it in a type preference object, and also the built-in Kotlin extension is not working properly. So we had a kind of hard time dealing with nullable numbers. So this is something what people should watch for, is that nulls can transform to zeros, and types, numeric types, behaving differently in different languages, although they are the same objects, because lots of the boxing, unboxing, and all the magic is done by the compiler itself. The next thing we encountered, or the next issues we had, basically, is also not really Kotlin specific. It's more about Java versus Clojure. So in Clojure, this is how a map looks like. There's the key one is the key, and value is the value, and there can be embedded maps. And Clojure is dynamically tied. It's a Lisp, and basically the code is also data. You can manipulate the code, the syntax tree. As I said, that our predictor library is called from the from the Clojure services, and because it's a dynamically typed language, we don't want it to have a typed interface because it would be extremely hard to interface with. You remember the Clojure code, the interop code, and it was not really simple to call a named Java function. So we had a typeless map, and then we take what we wanted to have from the map, and then we make our predictions, and we return with a score. Actually, the map what we get from Clojure is a Java util map. So it's a normal Java map, and because of the Kotlin compiler, we see it as a Kotlin map on the Kotlin side, so we can have all the nice functions and functional interfaces and everything. But we had an issue, so the resulted feature vector, what we extracted from the map, was empty. So to debug, I was printed the map, and I found that everything is there. So there is the key, there is the value. So I didn't understand what's the problem. So I tried to serialize it to a string, to a JSON string, and I checked the JSON string, and the JSON string also had the key, had the value, and everything. But if I check that it actually contains the key, the result was false, and it turned out it's because the Clojure map didn't have strings as keys, but those are keywords, which is a special language construct in Kotlin, in Clojure. And because Clojure developers are so natural with that, they don't even mention it, or it was not coming up during the talks. So we just had to convert each of the keys into string before, but it was it was a weird thing, because if I just printed the values, they all looked okay. They looked like strings. What about Scala maps? So Scala maps are a bit more tricky. There are mutable and immutable maps, and especially immutable maps are nothing like Java util maps. So you always have to convert back and forth from Scala to Java or Scala to Kotlin. But so this is a Scala map on the top right. It's just A to 1 and B to 1. And so it doesn't really different from any other thing. So this map interface can be worked pretty nicely with Kotlin lambdas, and the only thing worth other than this to mention is that if you don't have 2.11, then you will have a lot of trouble, because you won't be able to do this. And also, if you just wanted to serialize it with Jackson or any other serializer, basically without special Scala modules, then you will get some weird things on other content of the map. So yeah, Scala maps are not Java maps, and you can use the functional interfaces with SAMs. The last thing I would like to talk about is it's something which is rather technical, or it's more about compilation and not coding itself. Unfortunately, Spark has a lot of old dependencies what we have to provide. One of these old dependencies is Jackson, the JSON parser, what we also extensively use. And they use such an old version of that it doesn't have the necessary Kotlin module. The Kotlin module for Jackson is needed to be able to deserialize Kotlin classes properly. So we ended up with a problem that if we provide a new one, then Spark doesn't work. If we provide the old one, that we cannot deserialize Kotlin objects. So we solved the problem by shadowing the new version. So in our code, we can use the new shadow version, and in the old code, Spark can use its own old version. But the problem is that the shadow is not a Kotlin specific tool. It's a Gradle plugin, and it's a general Java specific tool, and it's not aware of the inner workings of extension functions. And unfortunately, it breaks something inside or under the hood. So if we have this extension function, the register Kotlin module, we are not able to import it. It's not visible in the Kotlin code. And unfortunately, Kotlin also doesn't allow us to use it in the Java way. So there is an object created for extension functions, this extension KT, and but it's not accessible in Kotlin because Kotlin thinks that that's an extension function, so it hides. But it's not able to use it as an extension function. The solution was to us that fortunately it is accessible from Java, vanilla Java, because the Kotlin compiler doesn't hide the class, so we can have a glue interface to have the interoperability. I think the take-home message here is that if you have magic on magic, so like the shading, which is already magic, like renaming packages, and the extension function, which does not exist in pure Java, then you can have troubles. And sometimes Java is actually able to help out Kotlin code. Just one word about the machine learning library. We try to open source it. The target systems are basically Spark and JVM / Python on the training side. So you will be able to train a model in any of these environments and make a prediction in JVM or Python. And you can do it across the system. So you can train a model in Spark and you can create predictions with it in Python. We don't have an exact roadmap yet. We are actively working on this. Now finally, what are I think the key take-home messages from this 3-year journey that we had is that one-way interoperability is easy and okay, but try to avoid two-way interop when you call Kotlin code from Scala and vice versa at the same time. Also, sometimes Java is just there to help because it doesn't have all the magic these modern languages are putting above Java. And that's also true for types. So arrays are basically the same in every language, and they also don't do type erasure, so they are very useful to pass around the collection data. And also, like I said with Java util double, it is a reference type everywhere, and so it works the same way in every system. And also, extension functions are very nice because if something is technically possible, we can hide the ugly code behind an extension function, and it looks nice from Kotlin. You can find me at the fireside chat at the end of the conference, and you can also check out the code and the slides at GitHub. But if you have any questions, I will wait a few minutes in the chat to answer those.